Already some word resonance you have come across. Resonance where, like if you go for the tube, organ pipes, this will be a tuning fork. There's an organ pipe, no? From where the energy for standing wave in the organ pipe will come? From this tuning fork. So shall we call this as a source? Supplies energy, and this organ pipe accepts that energy. So when the resonance occurs between the organ pipe and the tuning fork, then the maximum transfer of energy occurs from the source to the organ pipe. Then we'll get a maximum sound. So I think you look at the blowing of whistles. Some people will try to blow whistle. They're unable to get sound. Some people will blow whistle. They'll get very easily. The reason for that, because what is the source? The vocal cord. And what is the organ pipe? The lip, the tongue, or the jaws, everything will become organ pipe. And the air with which what you blow, the vocal cord inside that one, that will become a source. So the frequency at which vocal cord is vibrating, if they're equal to resonant frequencies of the organ pipe. What is organ pipe? Suppose a person blowing a whistle. What is organ pipe? It's mouth. That one altogether is jaws, tongue, this one, that lips. Everything will become organ pipe. So when the resonance occurs, then maximum sound will get. So this is what you have come across in the sound here now. So this is source. So when there'll be maximum transfer of energy from source to the load, this organ pipe will occur. So when these two are at resonance. So shall we put in one simplest way? At resonance, there'll be maximum transfer of energy from the source to the load. What is the load? Organ pipe, or the one which will absorb here. One which will accept. This will supply, this will accept here. Similarly, we are going to have here some sort of like a resonance ideas. So go back to some problems we have done where, as we vary frequency in AC circuit, can we control power dissipation? Answer is yes or no. Yes, by varying, because the what is the average power? The average power depends on what parameters? The average power, P average, is equal to IRMS, VRMS, cos phi. Cos phi depends on what? R by Z. And impedance depends on what? R square plus XL minus XC whole square. XL, XC in turn depends on what? Omega L, X is 1 by omega C. So by varying frequency of source, can I control the power dissipation in the circuit? By varying omega, I can vary XL, I can control the XL and XC. By controlling XL and XC, we can control the power factor. By power factor, the average power dissipated. So by varying frequency of source, I can see that the power dissipation, how much in the circuit. There's a basic idea is what, which I'm going to apply here. Now this is a source, VRMS. So here, let me take a components here. There's a resistor, inductor, and let this be capacitor. R, L, and C. The current flowing, let it be IRMS. How voltage and current here? So everywhere, I'll just show first current. They're in series, so it will have zero phase. Across resistor, how voltage and current are in phase. Across inductor, the current lags the voltage. So therefore, we show VL like this. Current lags the voltage. And across capacitor, current leads the voltage. I think series parallel things are a little bit different way of representing phasor. Here in series circuit, what is the reference? The current is the reference I'm taking. In parallel circuits, the applied voltage will become reference. So from this, the phasor diagram, just like this, we'll continue with what all we know it. I'll take it out all this content. Now first, we'll write expression for This we know. So this will be VR, VL, VC, and somewhere I'm just assuming VRMS like this. So from the voltage triangle, VL minus VC, VR, and this is VRMS. From this we'll get the impedance triangle. Now let's write expression for current I. So IRMS is equal to VRMS by Z. So this is VRMS. What is impedance? Z is equal to R square plus XL minus XC whole square. Let me expand this. Omega L 1 by omega C whole square. Look at now. The current flowing through this branch, or current flowing through the circuit, it depends on omega. Now I'll vary the frequency. I'll start increasing from 0. I'll either keep on increase the frequency. What will happen to current? What will happen to current? So first, prior to that, we should know how all the quantities are related with frequency. No? XL, XCR, how the various quantities are related. Let's take the graph here. No. X-axis is what? I'll take the frequency. Then first, what is XL? XL is equal to omega L, or this is 2 pi FL. So it should increase linearly. So shall we put it? This is XL. Then what about XC? XC, we have the equation will be like this, no? 1 by omega C or 1 by 2 pi FC. Rectangular hyperbola. Rectangular hyperbola, and moreover, it is a XC, XL and XC will be 180 degree out of phase. So that I will. This what all I'm plotting. There's a one simple basic idea. Please do remember this one. So it will be f equal to 0 at f equal to 0. We'll start plotting the graph. Look at this one. F equal to 0. What is xc? Will be infinite, no? And as the increased frequency, xc value decreases. And how xl and xc will be 180 degree out of phase. So therefore, some books they have shown the curve xc here. So, but it has to be shown it here. And f equal to infinity, it will become 0. So therefore, the curve will start. It's a rectangular hyperbola. I don't have space here, so okay. So what is this? This is XCM. Only I'm showing here. So this is XC, and this is XL. What about R? resistance, will it change with frequency? No, it remains fixed here. So the value of R is, take the solid one. So this is the resistance. Let's plot the current. What about the current?
Increase and decrease.
At one particular value of frequency, XL can become equal to XC, no? Then the current will be maximum. Then XL very much greater than XC, current will be less. XL very much greater than XC, current will be less. So here, look at the value here. At lower frequencies, XL will be greater than XC. At higher frequencies, XC will be greater than XL. And at one frequency, XL can become equal to XC. So where this quantity becomes zero, where the reactance becomes zero, current will be maximum. So what's happening to current? Current is going to increase, then it's going to decrease here. Becomes maximum, then decreases. So it's a rough diagram. One more. And it need not be symmetric. It need not be symmetric. So this will be the expression for current. IRMS, if you want IRMS, or you can write only maximum current. So like this, when I plot all the things, I'm getting the curve like this. So at one particular frequency, I'll call that as resonant frequencies, FR. In books, they call that as F0. At one frequency called a resonant frequency at which current will be maximum. I'll call this as I0. Any of the symbols you can apply, or IM, again you'll get confused with maximum value of current, that one. So let me call that as maximum IRMS, that is which is flowing here. So what do you mean by this resonant here? Means as I vary frequency of the source, the source will be supplying energy to the circuit. Then the energy supplied by the source to the circuit will be maximum when the frequency of source becomes equal to resonant frequency of circuit. Similar to what is organ pipe? This is organ pipe. What is a tuning fork? This is a tuning fork. So we just call this a source. This is a circuit. So when there will be maximum transfer of energy from the source to the circuit at resonance. the basic idea, nothing big. So how to calculate that resonance at resonance? I'll put everything in one page here only. Yeah, we'll see, you know. So at resonance, XL will become equal to XC, which is omega naught L, omega naught C. Omega naught square equal to 1 by LC. So what is the resonant frequency will be? F naught equal to 1 by 2 pi LC. And now you can ask questions, sir, how XL will become equal to XC? The net reactance will become zero. That's what the graph I'm showing. You look at this. This is having XL and this is having XC. When XL becomes equal to XC, because always XL minus XC must be, XL minus XC is the net reactance. So therefore it's better to show XC like this, reactance, capacitive reactance. This is inductive reactance. Some books they have shown this here, XC. Okay, nothing wrong, but again, little bit justification will be very much problem. So how XL plus XC gets added up, it should become more. So therefore, the XC should be, according to the thing, it should be drawn here. In the fourth quadrant, it should be rectangular hyperbola. Now this is a positive XL. This is XC. The net resultant, net reactance here will be 0. Now what about here? Capacitive reactance will dominate here at this frequency. Here what will happen? XL now has become more than XC. Curve that equal, we have to show it. Any good graphical questions can be asked for you. You be careful. No, I think it's this distance should be equal to this one at resonance. Just before, before resonance, you see that one, which was dominating capacitive reactance. XL minus XC. XC is greater than XL. After resonance, you see here. Now XL has become greater than XC. So therefore, how the circuit will behave before resonance for frequency of source less than F naught? It will behave like a lag circuit. Here it will behave like a lead circuit. The same circuit. And what about here? At this particular point, it will be a pure resistive circuit because net reactance is 0. It's a symbol. Everything I'm measuring RMS only here. All the potentials here measured is RMS. You write VL or VL RMS, both are same. It is understood, no? If I write only V, you'll get confused. That's why I'm writing VRMS. Huh? Okay, this is about the resonant frequency, lag circuit and lead circuit. What is the power factor?
The first one is lead circuit, sir.
First one is lead, no? Capacitive, this will be lag. Yeah. Symbols. For F less than F naught, it's a lead circuit. XC will be greater than XL. So we'll write it all the things. F less than F naught. XC greater than XL. So therefore, what is the power factor? It will be lead. Then what is the formula for power factor? Again, the same formula, no? Cos phi R by Z. The impedance you have to calculate this one. Similarly for F greater than F naught. XL will become greater than XC, then it will become lag circuit. Then power factor, again the same formula. We are not bothered about F greater than F naught, F less than F. We are bothered about at resonance only. At resonance only, there will be maximum, current will be maximum. You check it here now. So now let's come for third case, F equal to F naught. The current here which is flowing will be maximum, which is equal to VRMS by R. What about current in this case? Current which is flowing will be IRMS equal to VRMS by or this is equal to Z, where Z will be greater than R. So definitely where current will be maximum, Z greater than R. So let me write only in terms of that. It'll be easier for you. Tell me like where current will be maximum. At resonance only it will be maximum. It's sir, how do you can show that this graph will be like this only increasing, becomes maximum, decreases? I have enough proof here. For F less than F naught, check it here. What is the impedance will be greater than R? because XL will be greater than XC. Sorry, XC will be greater than XC. So therefore the impedance will be greater than R. For F greater than F naught, XL will be greater than XC. Then again the impedance will be greater than R. So compare this value, IRMS and IRMS max. So definitely here what when the impedance is least, no, this will be. So I'll get the current at resonance only will be maximum. So altogether, if maximum current flows, who will dissipate power? Only the resistor, no? So therefore, what is the maximum when the source will deliver maximum power to the circuit at resonance? That's the basic idea of this one. Now we have to work out few lot of concepts are involved in this. This is about the, I think I can, this much is available, the total everything. What about the power factor cos phi? Where it will be maximum? At resonance only. At resonance only. So I want to plot power factor versus frequency graphs. Let me go for different types of graphs here. Let me put it here at resonance. What is the power factor? Should be equal to 1. And what is the power dissipated? Will be maximum, which is equal to how much? IRMS into R, or IRMS into R is what? VRMS, no? So VRMS into IRMS maximum. Which all information is available, you can calculate the power. So you check this power will be maximum at resonance only. So word at resonance, this is everything what we're discussing at resonance. At resonance, there'll be maximum transfer of energy will occur from source to the circuit here. In the circuit, we will take the resistance. Now let me plot power factor versus the frequency graph.
Same graph.
The same graph, no, it should be. You should be very careful about the possible types of graphs here. This is a power factor. That is what cos phi, and it will be equal to 1 here. This is very important here. It cannot be greater than 1. Maximum value will be equal to 1. And this is the resonant frequencies. Lead circuit, this is a lag. What about the, as a very resistance, any changes will come? I'm not going to disturb. So what should be the value of F naught? It depends upon this particular thing. L and C will determine what should be the resonant frequency of circuit. So what I do is, I'm going to keep L and C fixed here. I'm going to change the resistances. Let's see how possible a graph will come here. So there's a resonant frequency because L and C are kept fixed. So resonant frequency will not change. I'm interested only in the, first I'll put resistor R1, then the resistor R2. How the graph is going to be, sir. So first one. Can you say anything about what is this? I plotted current for different values of resistance. So which should be the R1, which should be the R2? How to determine that one? Look at the curve. So one more, the impedance, total impedance can be plot. total impedance in this. Magnitude of impedance, mod of Z. Yes, one more we can plot it. I think any color. Yeah. Mod of Z will be it should not cross that XL, because impedance is what, like R and XL will be there. Of course, R will get added to XL and here XC will come. R plus XL, no? So the value will be a little bit, somewhere here we'll show it. Yeah. So this is what mod of Z. Again, we'll give the name. Why mod of Z? Impedance is, or say impedance is what, R square plus XL minus XC whole square, no? But still it's practice of writing mod of Z, that one. So let's come for that impedance. I'll take help of this one. So now we know current is maximum, then impedance will be minimum. The impedance will be minimum. So then what is the formula? I1 max equal to Vrms by R1. I2 max equal to Vrms by R2. So this I'll represent I1. This as I2 max. Now look at here now. So definitely R2 should be greater than R1. No? R2 should be greater than R1. If R2 is greater than R1, then I2 will be less than I1 from the graph. This is R2. So therefore, how the impedances, if I plot impedances for this, because at resonance, what is the impedance equal to? Only the resistance. So when I plot this graph, oh, you will get impedance less. If the resistance less, current will be maximum. Then one more curve. Blue color, I'll take it. Where the blue color? Is it okay now? It can come. I'm just showing the rough diagram. It should be like this. So now we should be the I1. This should be the for I1. And this I'll call I2. So there's impedance. This should be the Z2. This should be the Z1. So with this, what we can do is Z1, this should be equal to, and look at this. So where R1, R2, I should show that R1, R2, we have to show it here. This will be the, it is messing up with this one. Yeah. Which is R1, which is R1, which is R2. This should be the R1. This should be the R2. And this is I2 max. Try to make observation, nothing big. Just if I vary the resistance, the graph curve is going to change. So when Z2 is equal to R2, so the curve will come, no? And this current will be maximum. Here, this is what I2. And when Z1 equal to R1, then the current will be maximum, that is equal to I1 max. Is it okay? Representation of that. So as you vary, as you increase the resistance, and with this, what we can say, R2 greater than R1. Okay, looking at this, as you increase the resistance, what will happen to the sharpness of the curve? I'll put one more, so it will be. No, as you vary this one, because I'm bringing the word sharpness. No, as you increase the resistance, what happened to sharpness? Which curve is sharp? I'm using word sharp. So I think this is more sharper. No, the red color curve is more sharper. Particularly when you plot in the graph, no, the curve will appear like this. The sharpness, what happened of the curve, resonant curve, depends upon the resistance. As you decrease the resistance, sharpness will increase. As you increase the resistance, the sharpness will decrease here. Sharp, I think pencil, sharpener, pencil. With a sharpener, we do it, no? So if it is how sharp it is, the curve is also, it is, this red color curve is more sharper than the green color curve. So what happened to as you decrease the resistance, the sharpness will increase, or as you increase the resistance, the sharpness will decrease. So this sharpness, technically we'll call that as like a quality factor. To express this sharpness, no, I'll bring a word called as a quality factor. Now, where do we use this? All communications, what all we have, mobile, television, everything, no? Where all, if you want to select a desired station, desired signal, the series resonance, it is brought here. So if it is having sharpness is more, then it's said to be a very good RLC circuit. The sharpness depends on what? The sharpness depends upon the resistance. Technically, we just put it things like this here. So now, the measure of that sharpness is nothing but the quality factor. So let's see that how that quality factor on what all parameters it depends. So they may ask you any graphical use. I think so many things are there. They may ask you first graph, this one, then next again the power factor, then impedances, current, everything is included here. So you must go through this particular graph before advanced exam. Okay, let's come for the sharpness, what we define it.